Hi everyone, in this video here, we are going to make use of GeoGebra to see how Newton-Raphson works to find a good approximation for the solution of an equation. And in here, we are referring to some equations that the solutions happen to be very tedious and it seems to be impossible to be solved manually. For example, I have an equation here, e to the power of 0.3x plus 0.1x minus 1.1 equal to 0. To visualize the solutions of these equations here graphically, what we can happen to do is that we rearrange the equation in such way that, as I show you here, all the terms I leave it on the left hand side and then equals to 0 on the right hand side. Then I consider the left hand side, all the terms on the left hand side here now, let it equals to a functions, and these functions here, I plot the graph. And from the graph, the x-intercept of the graph will happen to be the solutions of these equations here. So in other words, if I'm able to find out the x-intercept of this graph here, therefore I can get the solutions for these equations here. And now we're going to make use of the idea of Newton-Raphson's to get the solutions here. And we're going to do by graphically, to visualize by graphically instead of calculations. Before that, what is actually Newton-Raphson methods happen to do is that Newton-Raphson methods is actually trying to use the point along the graph to form a tangent line that happens to be touched on the point along the graph. And we consider the tangent line that happen to be formed is almost merged with the graph, or I say approximate to the graph, to the curve, in such way that you will happen to find out that later the tangent line that we happen to form, it happens to have a x-intercept almost the same or exactly the same as the x-intercept of the graph. And from the x-intercept of the tangent line, we happen to find out the solution of the equation, or it is more appropriate to say the approximations of the solutions of the equations. And now, to start our Newton-Raphson methods to approximate the solutions of the equation or the x-intercept of the graph, we need one initial value. And graphically, we can see that the x-intercept of the graph is happen to be in between 0 and 1. So usually it happens in this case here, we will consider the first approximation as the midpoint of 0 and 1, or the average of 0 and 1. So in here, I will consider the first approximation where I happen to label it as initial x here with 0.5, which is the midpoint between 0 and also 1. Then let me zoom in the diagram so that we can see the 0.5 of x value 0.5 before we go on further to visualize how does Newton-Raphson methods happen to works in approximate the solution of the equation graphically. So in here we see that x equals to 5 on x-axis is at this point here. And obviously, this is not happens to be the solutions of the equation, where 0.5 is not the x-intercept of the graph. So by graphically, what actually the process happening is that we consider a point on the curve with x equal to 0.5. So this is the point. And at this point here, we form a tangent line. In here, you shall see that the tangent line happens to be this straight line here. And you find out that this straight line here, at this moment now, it seems to be merged with the blue line. And it seems to be also the x-intercept of the red line, which is the tangent line, is the same as the x-intercept of the curve. But is that true or not? Let us happen to see further. So this is happen to be the x-intercept that we happen to visualize at this moment here. And let us zoom in to see. Is that happens to be true to happens, where the x-intercept of both of them is happen to be the same. So as we zoom in, we happen to see that the x-intercept of the tangent, which is the red line here, is not the same as the x-intercept of the blue curve. So now at this moment here, this is still not a good approximation. So we need to perform our calculation further. And based on this software here, I suppose I'm able to find out the x-intercept of this point here, of this tangent line here. If it happens to be 0.25068, if I want to correct to 5 decimal places. Then continue. This resultant x value is not still not a very good approximation for the solution of the equation. So what we do the next now is that, let me zoom in the diagram further. Let me zoom in the diagram further so that we have a clearer vision on what will happen next. So now when the time we zoom in the diagram, you can see that the two intersection is actually quite far away. And now what we're going to do the next now is that we proceed from this point here. We find out that what is the corresponding point on the curve in blue. We happen to have the same x value, which is the x value of 0.25068. So in here, I will just happen to proceed by using the setup here, where now, just now the initial x is the first approximation, the x1, 0.5. Now I continue the calculation where it's happened to be a repeating process, where now in here, the initial value, I will happen to change to the result that we find out just now, 0.25068. Where later, you will happen to find out that in here, it will happen to form a point corresponding to this x value on the blue curve, and as well as a tangent line for this corresponding point will happen to be formed. And let's see, this is what happened. So if you happen to observe carefully now, actually the red line that happened to form, which is the tangent at the point that I have a red cross here. At this moment, you see once again you see the red line is almost merged. Or I should say, seems to be exactly merged with the blue curve. And again, if they merge, by right, they share the same x-intercept. And therefore, the x-intercept of the tangent is supposed to be, happens to the solutions of the equation. But once again, let us investigate further by zooming in to see whether is it true or not. So let us zoom in to see closely whether these two graphs here is happen to be merged with each other or not. So as we zoom in and in, you happen to find out that although just now it appears that they are merging with each other, but now at this moment here, you happen to find out that they are actually still not happens to be intersect at the same point. There is still happens to have gap between them as I happen to zoom in. Then next, what I do now is that I will repeat the process again. Now I use this resultant x value, substitute into the initial value to form another tangent line, where the tangent line will happens to be at the tangent line will happen to pass through a point on the curve with the x coordinate 0.24319. And let me now insert the value 24319. And now later you happen to find out that from this intersection point here, later you will see an arrow point at the corresponding point that come with the same x coordinate on the curve and form its corresponding tangent as you see now. So this is what's happening now. And now once again you happen to see the red line is happen to be almost merged with, or I should say again is apparently merged with the blue curve again. And I won't continue to zoom in any further. By right, you see the initial value that we happen to insert in, compare with the result that we have, which the result is referred to the x-coordinate of the intersection point. It happens to be almost the same. When the time we round up into 4 decimal places, by right, you happen to find out they happen to be equal to each other, where when the time you round off, you got 0.2432. So by right, at this moment here, we can come to the conclusions that 0.2432 should be the approximate solutions for the equations. Of course, if you want to continue the calculations, I can proceed even further, but maybe it's meaningless for me to continue to zoom in the graph, where in the graph here, maybe you won't able to see any significant gaps between them. As you can see, the decimal is different by 0.0001. Even I zoom in even further, it seems like I have limitations on that. But let us see in diagram wise to see how it's happening. So if I go on to proceed the calculations, let's say now I have a new initial value, refer to the result just now. I substitute with 24318, and let's see what is the result. You happen to find out now, this is happen to be the result that I have, where you can see the initial value and also the resultant value. There happens to be almost, not to say almost, they are exactly the same as apparently up to 5 decimal places. So by right it is the end of the approximation. It's meaningless for us to continue further, because you will see that even I insert another times with 24318, then the result will come out with the same answer. So by right, the approximations end here. And later in the calculations, you will happen to need to observe the stopping criteria that we need. We are not going to stop at the moment that we have exactly the same value in calculation wise, but we try to see the stopping criteria in the sense of when the time we happens to have the round off values is the same. Like just now, by the time I have the case of 24319 and the result is 24318, if I round off to 4 decimal places, then by right they have the same result, then that's a stopping criteria for us to consider the approximation of the equations. So therefore, I will stop the video here, and I hope that it happens to give you a clear idea on what is going on in the Newton-Raphson method, where we try to make use of tangent line that pass through points on the curve to estimate the intersections, the x-intersections of the curve, which is corresponding to the solution of the equation that we desire. That's the idea going on. And along the calculations, you happen to see we're doing repeating process because we are using the linear approximations, which is the tangent line, again and again along the calculations. So that's all. Thank you.